Alright, hello everyone. Today we're going to be doing our Machine Learning Zero workshop, where today we'll be mostly talking about different machine learning algorithms. Oops, sorry. Yeah, we'll be mostly going over the machine learning algorithms that we are going to teach about, kind of the machine learning workflow, and just kind of giving you a high-level overview of what to expect when working with machine learning. And this will not be an in-depth conversation of individual algorithms or, for example, like neural networks, but just kind of a teaser and introduction to it, so maybe you can start working on it by yourself. So yeah, today we'll be working on our ML0 um, Jupyter notebook that can be found on our GitHub, and yeah, and also if you please sign in using the link in the description. Let us know who is coming out tonight. Give an idea of yeah. Anyways, so I'm gonna give a couple minutes in case anyone's joining us late. But yeah, so feel free to listen along. Also, this will be posted to our YouTube channel later tonight. So if you have to bounce at one point, you can definitely come back and keep watching. I believe next week we'll be doing ML1. ML1 is going to be going over the actual implementation of it. So today we're just talking about like high-level concepts, but next week we'll be actually talking about like, okay, let's actually code some of this stuff. So that's what we'll be doing today. So I'll give it a couple more minutes. But yeah, I'm excited to talk about machine learning. Oh, and additionally, I think today would be best um, if people like interact in chat. So if you have a question, please post it in chat. I'm gonna try to look at it every 5 or so minutes. Yeah, so if you have a question about kind of what's this used for, or like maybe I didn't explain something as clearly as possible, or I need to go back, feel free to put in chat. I definitely appreciate interaction. Definitely, yeah, it's good. It's good. So, yeah, we'll give it like maybe at 7:04. Give it like 2 more minutes, and then we'll get started. One second, guys. Let me fix the link in the description. Oh, and the GitHub link. If you do GitHub/DSI-UFL, you should be able to find it. That's where all of our repos and workshops are in. So Python, R, all that kind of stuff. Um, yep. And if you need any help, if you can't find it, then I can definitely help assist further on. Oh, okay. Okay. So, one second again. Sorry, this is being a little more difficult. Okay, so in chat, I just posted our link. That should be the updated version of the thing. So yeah, if you please sign in at that link, post it in chat, I definitely appreciate it. And yeah, we'll get started here. Maybe a minute or so, let people sign in. But anyways, before we get started, I guess I'd like to get kind of a feeler. If you want to, please post in chat kind of your relative experience with machine learning. Have you done any at all? Has it been maybe some experience in class or maybe research, or maybe get an idea of where people are starting at to get maybe better teach the class today. So, yep. All right, cool. So Christopher Perez says took a basic course on Coursera course on it, did some applications with MATLAB. All right, cool. So has some coding experience, and just curious, Christopher, what type of machine learning was it? Was it like linear regression? Was it decision trees? Was it KNNs, or was it like neural networks? All right, I think we started now though. So today we're going to be talking about kind of overview machine learning. So we're going to cover all the basics of machine learning. We'll just discuss kind of the principles of machine learning, how to properly clean and format data in order to implement these models. So we're going to go over some basic ML models, but mainly the theory behind them. Implementations will be discussed next Monday in ML1. That's where we'll be coding it. So yeah, so machine learning is a subset of artificial intelligence that relies on the idea that machines and they learn from them. It evokes a process that uses to identify different patterns in a given data and make decisions without human intervention. Machines have a number of applications in the field of data science, including image processing, classification, language processing, and learning association. So, for example, image processing could be something like I have a pictures of cats and dogs, and that could be something like figuring out whether it's a cat and dog. So that'd be under image processing and classification. Language processing would be something like, hey, if I take a tweet, what's the sentiment behind it? Are they happy? Are they sad? That'd be kind of something like language processing. And learning association is something about basically learning how things are related to each other. So what's the association between them two? But based on the graph, you can kind of see that artificial intelligence is kind of this overall idea that machines can learn some type of latent relationship, but machine learning is kind of this subpart where we have supervised, which is the idea that you have data and you have some type of target where you're trying to get, given some data, produce the same target. Unsupervised is like something like clustering algorithms, those kind of things where you don't have a target, but you're just trying to like group things together in a certain way. And then deep learning, which is kind of the new hot topic, is using neural networks in specific ways that are to create really like complex relationships and get really good results depending on the application. And then natural language processing, you see a lot. You see it's becoming more and more popular today. That's the idea that you can take text in and understand what it's saying, or the machine can understand what it's saying. So that can be something like Q&A bots that maybe a company will have for customer service. It could be something like I said, sentiment analysis. It could be all kinds of stuff. I mean, I think one of the most famous examples currently is a GPT-3 model developed by Elon Musk's company OpenAI, where it's you can give it some type of introductory sentence and then it will kind of fill in the rest from there. Expert systems, I believe, is something like give an option that gives you the best result. Speech is kind of what you think it is. You can talk to it, like for example Siri, and it understands, can convert speech to text, and the opposite, obviously. Vision is also a really popular field for image recognition. So this could be, for example, like I said, like the cats and dogs example, but also say you're taking a picture of a check that you want to submit to the bank. Image processing or image recognition is that kind of thing, and then machine vision is kind of in that same thing. And then robotics and planning, as they kind of say, robotics is AI, like whatever. That's not what we're too focused on. But yeah, so in a blurb, essentially all of it, no matter what, starts with data, and data is the most important part of any machine learning, and that's what you'll spend a majority of your time working on. Even though the algorithm is a cool part that everyone wants to work on, I'd say approximately 60 to 85% of your time will be working with data itself. Just because if you feed the machine learning algorithm in either a small amount of data or a bad representation or bad data, it's not going to be able to learn very well. So it's like, think if you're trying to teach a child, you need to, have good lesson plans in order for it to learn well. So yeah, during training, the model will start recognizing patterns and relationships from the data that's given, and then it can make decisions in the future based on that. So you can kind of think of it as the data as experience, and as you show them a variety of different experiences, they'll learn these patterns and relationships, and then in the future be able to basically see those same patterns and then replicate them, kind of like what humans do. So now I'll kind of give you an overview of the kind of steps in the machine learning model creation process. So it's not just fit a model. It's actually take a little bit of time before we get to that point. So and like I said, these steps are not set in stone. Sometimes an ML engineer will carry out um, these steps maybe in not the exact order. Sometimes, for example, in the first step, data cleaning formatting, that might be done by a data engineer. It might be given to them. There's all kind of things that they might do. But this is kind of, we want to give you a high level overview. Before we start, let me check the comments. Okay, yeah. All right, cool. So the first step in machine learning pipelines or kind of model creation is data cleaning formatting. So this is kind of one of the largest steps depending on the noisiness or messiness of your data. So a lot of times when you're feeding in machine learning data, it has to be pretty clean, as in the fact, depending on what you want your model to be. For example, say you are uh, doing image recognition, where you're feeding your algorithm images, and you want to be able to determine like whether it's cat and dog. Well, for example, if you have a big data set, you want to make sure that the images are centered on the cat and dog, and you want to make sure that they're not like extra stuff in the background, or like make sure it's clean, right? And it's easy for you to tell, right? Another example would be, say you're doing um, like financial records, right? And there's a lot of like weird like input errors, that kind of stuff. You want to kind of remove those as well. You can't have a I don't know, a negative like report income, right? So those kind of things you want to make sure that remove outliers, remove things that just don't make any sense. There's a lot of examples of things you want to do. If you want a better idea for specific things like text editing, image recognition, definitely Google them online for sure. But yeah, so that's the first step, kind of data cleaning and formatting, getting your data into a workable space. The next thing is exploratory data analysis, also known as EDA. So you have your data, but you just can't plug it into your machine learning algorithms immediately. You kind of need to understand what's going on here and make some understanding to help you later decide what machine learning algorithm or model you want to use. So for example, you can use visualizations to see relationships between two variables, or using correlation plots or box plots, or all those type of understandings. Like for example here, they say like construct linear models to determine relationship between two different features. For example, maybe you have like age and height, and you want to, or like age and like health, maybe, I don't know, something along those lines. You want to try to see like if there's a relationship. And yeah, it's very important because you'll be able to determine like the purpose of your model before you design one. It's kind of the way for you to like kind of see what your data is doing. Make sure like it's also a way for you to like, hey, so say you you use your EDA or exploratory data analysis and you find some issues with your data, you can then loop back to step one again and say, okay, let me fix that, and then you kind of repeat this process. So it's kind of a way for you to check your data, and also it's a way to you start seeing some relationships between your data and kind of help you understand what's going on. The next step you want to do is you want to think about what type of model um, you want to do. So we'll go back up here. So example, say we're doing machine learning and we want to think about, okay, do we want to do supervised learning, unsupervised learning, or deep learning? So a lot of times this can be sometimes a tricky problem, because sometimes all the time you can approach a problem in many different ways, but most of the time there's an optimal solution. So this is the start. You want to think about, okay, do I want to make this a supervised problem? Do I want to make this deep learning problem? All those kind of things. And then you think about within each domain, for example, vision or NLP, or also known as natural language processing. So, yep. And then next, yeah, they talk about here. So I kind of repeat what they say. So the goal of supervised learning is to determine a function. So there's some function that maps the inputs to outputs, and you want to be able to have that function so you can then predict future results. So the whole point of supervised learning is to say, if you give me these data points, I can tell you the future. So it's predictive, right? So it uses data to come up with a function that fits the data. That way prediction can be made when the model is introduced to a new data point. This type of machine learning requires that data have inputs and sample outputs for each data point to use to train the model. This is a popular method. This is probably the most popular method of learning used by data science today, implemented in the field. So, for example, when I worked at a financial company this past summer, a really good example of this was fraud detection. So, if someone steals your card, how does the credit card company know to deny the transaction even though you didn't tell them? This is part of supervised learning where they have a bunch of transactions and where each transaction is marked as fraudulent or not, and then it's supervised learning to be able to understand it even without it being told. The next big cluster or big type of machine learning is unsupervised. Unsupervised learning is determined hidden patterns in data from unlabeled data, where they're just input points but no outputs. It's mainly used in processes for anomaly detection or data pre-processing. So this can be like, for example, I talked about cluster analysis, where you have maybe a group of people and you're trying to figure out, they may look all homogeneous, but maybe you can find subgroups within it. You can do, for example, like anomaly detection. That's another one. There's all kind of things in unsupervised, but maybe in practice it's not used as heavily as supervised. And then reinforced learning is kind of a mix between the two. So reinforced learning, you want to have some type of function that tells you how good your result is, and it uses trial and error to come up with the best solution to the problem and react to the environment they run in. So, and it's really using games, right? So maybe it's in a game of, you're coding for a game of like, I don't know, tic-tac-toe, right? And the objective of the game is to obviously win. And so in the first generation, it'll do seemingly random predictions or random actions, and then when it fails, it will update and learn from that, and then it'll keep updating over and over again when it keeps failing, and then eventually it'll start learning, and then when it learns how to win, it'll keep trying to do its actions over and over again. So that's kind of reinforcement learning. You see a lot in games. I think, I've been reading that reinforcement learning might become just as popular as supervised learning, but it's still kind of in our research. But yeah, we can kind of see supervised learning here. So I'm gonna take a stop. I'm gonna stop for a second and see if anyone has any questions. All right, I'm gonna move forward then. Okay, so next thing is so creating our features and targets. So we talked about, so first I'll let you say that we're gonna be doing unsupervised learning take, just because that's probably the most common type of machine learning and probably may or can be the most useful, especially I think, or most commonly used. So features are basically our inputs and targets are our outputs. So given certain features, we want to predict our targets. So let me read this. So the data we use in ML can split into features and targets. While mostly used in machine learning, is key to training most ML models. Features are all the data collected for each data point, and the target is what you want to be able to predict about each data point. So basically, you can think of features as your X and your targets as your Y. So our example today is going to be determining if, given Pokemon stats, we're going to be able to determine if it's legendary or not. So, for example, if we have this data set that we included here, I think last week we used it for our visualization workshop. We have all that, like the name, the types, their total stats, which is a sum of like HP, attack, defense, all that kind of stuff. The individual results or individual statistics or stats, and then generation, and then our legendary. So this will be our target, while for example, like these columns will be kind of our features or inputs. So we'll read this here. In the above data, each row represent a data point, and the features would be all the columns represent the data points such as HP, attack, defense, etc. The target would be the column you're trying to predict. In this case, the legendary column. Once complete, the ML model will be able to take all the features above without the legendary column and be able to predict a degree of accuracy and whether or not the Pokemon is a legendary or not. So as you can see here, we can say the target is we just take this column right here, and then the features are everything basically but legendary column. And then we can see here it's just true or false. So basically this is like a binary problem, and this is under the classification sphere, which if we go back up here, I guess they're not, but like, supervised can be classification or regression, where classification is you basically doing a label, for example, like yes, no, false, false, true. It could be like cat, dog. It could be multi-label as well. So example, so you have numbering, you can do, predict the number 1 through 10, while regression is you're predicting a continuous output. Say, for example, you're predicting the price of housing. That would be continuous because it can be between 0 and, let's say, $10 million and any decimal in between that. So, yeah, so we're going to be doing a supervised classification problem using, or trying to predict whether a Pokemon is legendary or not based on its statistics. Alright, so next step is choosing the model. So now we understand what our objective is. We can choose a model. It's important to choose a model you want based on your objective, but it's not essential as it is to try to, whoops, but it is not as essential as it is to always be good to try to do different models to see which one has the best performance. So a lot of times you're going into it, you might have suspicions of which one will perform better based on kind of experience and kind of like, we'll talk about which models perform better where. But at the end of the day, most of the time you just want to kind of test all of them a few at a time and see which one just performs best. And we'll talk about how to judge these models. And yeah, so we'll go over kind of some of the basic models that are considered classical machine learning, supervised machine learning. And then we'll kind of end off with neural networks, which is kind of starts going into deep learning and more complex stuff. Before we get forward, let me check if there's any questions. Alright, yeah guys, so if you have any questions, please put them in chat. This is where we start going over algorithms, and yeah, this is a pretty important step. Alright, so k-NN, or k-nearest neighbors, is a pretty naive but effective algorithm. It works well when all the features have numerical values and there are low number of features. And this is, they call it recursive dimensionality. This is the idea that when you have, for example, a lot of features, which means like a lot of columns, or like different ways you can try to represent a data point, or like represent, but like like different types of data points. It can be really confusing for the model because could be yeah, it's just not, basically I don't want to get too in depth, but basically when you have a lot of features, for example, save an image and it's 400 pixels by 400 pixels and with 3 channels in it, you're going to have 400 times 400 times 3 different inputs, and that's can be very confusing to the machine learning because it's a lot of numbers. While a low number, like kind of what we have here, which we have, how many do we have? We have, oops, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 features, which is relatively small, so that's good. You can kind of fix the curse of dimensionality with unsupervised learning techniques such as PC and LDA. I'm not going to them today, but just kind of know that a high number of features is a problem for classical machine learning. Anyways, but for k-NN, all it does is basically plots all the points in an n-dimensional space where n is the length of the feature, the number of features we have, and labels them with their corresponding target values. The closer the user selects a k values, and then that k is basically how many neighbors it looks for. And yeah, so I guess let me explain it first, and I'll read about this. So first thing you do is when you fit the model or you train the model, you basically put all of your data points in your feature space, which is basically just think about, if a two-dimensional sense, it's just you apply your x and y points that you trained on. And then when you want to predict, all you do is you plug your point into your feature space, and then you calculate your distances to each point. And then the number of points you calculate to is based on your k value. So is k nearest neighbor, so if you have 5, you'll maybe select the 5 nearest points, and if it's like 10, so on and so forth. That's called a hyperparameter. So basically hyperparameters are your internal knobs that you can kind of move and you can basically like optimize this algorithm to be better or worse. Obviously you want to be better. But yeah, so for example, in our chance example, say this is our data point, and then say like these 2 are legendary and these 5 are not, and we use a k, k equals 3. You would see that these 3 right here, these 2 being legendary and this one not, this point would become legendary or predict legendary because these 2 are closest and it has majority vote. So that's kind of how it works. For example, with regression, which is continuous numbers, it would take the weighted average of these 3. So yes, but let me repeat. So The user selects a k value, which is the number of points it looks around, the k closest points, which is with the k is what you can tune. And then yeah, it does like a majority vote. So the k closest points, it takes the majority of, and that's your answer. Yeah, and that's basically KNN. So it's really straightforward. The math is pretty straightforward. It's just distances. Obviously, there are different ways to do distance. I think you can do like your L2 norm, which is like your square root of x1 squared plus x2 squared all up to xn squared. But there's other ways too. You can do different norms. You can create your own distance formulas. Yeah, I mean, there's all kind of things. These are all. That's another hyperparameter of KNNs. It's your distance metrics, right? But yeah, that's KNNs. I will say KNNs are great for certain types of problems, but they do require a lot of data. So you can imagine is that if there's holes in your data points and you plot a hole, it's going to select points that are really far away and might not be very accurate. So KNN needs a lot of data, and it also is, but it is good though, is because it can model nonlinear functions really well. So if you have exponentials or something really strange, KNN can perform it because there's no bias. It doesn't assume that it has to be linear or follow some type of um, like relationship, right? It's very flexible in how it predicts. So if you have a lot of data points, KNN is probably really good for you. Yeah, and I'll stop before I move on to random forests. And yeah, if you have any questions or want to repeat something or explain again, feel free to ask in chat. Definitely appreciate it. While I wait for questions, I think one thing to mention here is there's kind of this underlying concept of it's called bias versus variance. It's really important stats and also machine learning where it's kind of this trade-off where you incur basically error from bias and variance, and you can and it's kind of a balancing act. So say this is your variance and this is your bias. If you increase your bias a lot, your variance will go down, but you still kind of have you increase your error this way. So the best way to do is if you have a very complex relationship, you want something that's not very biased. So say for example, you have an exponential relationship underlying, and you're using a linear function, like a linear model. It's not going to perform well because you're giving it a lot of bias already. It's going to go up a lot. But for example, in KNN, where there's no bias at all, and it's okay to have a lot of variance because it'll like model relationship better. So bias versus variance is kind of this idea that you're going to incur error from either you have a lot of variance in your data points based on not really giving your algorithm any structure, or you're going to incur a lot of error from basically you stating that your data points or your relationship's going to be in a certain way and it's not. So that's kind of the way. So KNN is a very high variance, low bias problem or model because it doesn't force relationship to be in any given way. It's very flexible. Yeah. Okay. So we'll move on to the next one. So random forest is our next type of machine learning algorithm, but first we have to understand decision trees. So decision trees, as the name suggests, use a tree-like model to make decisions. In machine learning, they are used to allow models to represent decisions and decision making. Data can be converted into decision trees where features and their values are decided, where the branches and leaves would be, and the branches basically determine yes or no and make decisions, and the leaves are results, right? And so these would be your leaves on here. Their branches would be basically your decisions. So for example, here this is your problem number of family members. Greater than 3, you'd go down this side. Greater than 80K is married, and then your result would be down here. So these are actually really popular, I know, in business because they're really easy to understand no matter who you are. You can easily read this easily. And yeah, so the one thing you think about here is that basically they're making like linear cuts in your data set, right? So you're saying if it's greater than 3, over here is all going to be in this way, or all no, or all one type and another. So they're making just a consecutive linear cuts within your data set, and that's how it's getting your results. Um, Hello? Sorry about that. Um, my headphones just turned off. Can someone let me know where my mic turned off at? Don't post in the chat because I don't know how long I was talking for without audio. Um, I guess I'll wait. I guess there's a little lag, so I'll wait. Have I started talking about random forests yet? Okay, not too long. Okay, I'll start back at random forests then. So basically, random forests are basically a collection of decision trees where it uses bootstrapping technique. So just to repeat again, bootstrapping is the idea that you have your data set and you take random samples from it many times with their placements. So it allows you basically from one data set create many, and then you can fit a model each one and then aggregate the results. So yeah, and so we talked about the hyperparameter before of n or k and k and n. Well, now we have this like hyperparameter n, which is the number of bootstrap samples and decision trees we create. So for example, here we can think about it as we have tree 1 with one data set, this is tree 2 with another data set, and tree 3 another. And then what we do is that we basically, in a new prediction or a new data point, we run it through each of them, and then we get the result from all of them, and then we take the average of it. So say two of these two trees both predict green, or okay, here they go. Two trees, 1 and 3 predict red, and then um, um, tree 2 predicts green. And so overall we'd predict tree 3, as we can see here. There's also something else we should consider with bootstrapping that's maybe not required, but it's recommended, is that if we were to take the same data points and just resample each time, most likely we would split at this with the same feature each time based on which one's most important. What I mean by split is, here the feature would be number of family members, right? And it splits if it's greater than 3. So if you can imagine, this is the most important feature in determining what type of flat the person's using. You probably get a bunch of decision trees that are very correlated and very similar. That'd be a problem because it wouldn't get a lot of variance in these trees, and it wouldn't really be that useful. Basically, we're just fitting the same tree multiple times. So what random forests also do is that each time they randomly only allow certain features to be used. So what that does is that at the first level, it's not guaranteed to use the same feature every time because that best feature not might or might not be allowed to be used. That's basically a way to like reduce correlation between trees to try to get better averaging. So you can kind of think as random forest as like averaging a bunch of decision trees together to kind of get a really complex um, answer. And I will say decision trees are probably, I would say for most application, they're really good. If you use enough decision trees where you're n and you have a good data set, you can most of the time get really good answers out of it or really good scores out of it. I'd highly recommend this is probably the go-to at the moment for classical. Yeah, so any questions on this? This is probably one of the best ones we'll talk about today. Obviously, other ones have their own perks and benefits. Also, let's talk about bias versus variance. Um, this one again, if you think about it, it's making these, decision trees are using linear cuts, but since you're combining it together, you kind of reduce those or kind of remove them in a certain way because you're kind of taking the average of all three. So you can start getting more nonlinear relationships in them. So they're less biased, probably a little more variant because if you think about it, if you're, depending on what data you can choose, it will affect your average over time. So yeah, so I'll stop for a minute and take questions. All right, cool. Any questions? I know I might have cut out there for a second, so I don't want to make sure I didn't forget anything. All right, I'm not seeing any questions, so let's move on. So next one we're going to talk about is support vector machines. So these actually used to be, I think, a really big deal back in the 90s, I want to say, and they're still used today. Maybe not as much as they used to be because they've kind of been replaced by other techniques, but there's definitely something, when you're doing your model creation, trying to figure out which one's the best, you still want to run it. It can definitely be a good result sometimes. So SVMs, basically the idea is that you have this line and you want to try to find the line that has the maximum distance between the two data categories, right? So if you can imagine these data points on here are like legendary and these data points are not, you want to find the line or hyperplane as they call it, where hyperplane is like, if it's 2D it's just a line, 3D it's a plane, 4D it starts going hyperplane, and so on forth. But you want to find basically the maximum line or maximum distance between, or line, sorry, that has the maximum distance between each data set, or basically each target. So you can think about, you want this distance to be as large as possible, and basically you're trying to separate two classes. And that's basically all it does. I don't want to go into the math of it, but that's basically what Canaan's or SVM does. Yeah, and basically it starts off with some choice, and then it kind of iterates and tries to find the optimal solution. And so the one thing that kind of stinks about SVMs is that it requires the targets to be linearly separable, which means that you can put a line between the two targets, and there won't be any crossover basically. As you see here, that these are linear separable, but if you go down here, this is not linearly separable, right? Because you can't put any line here where on one side line it'd be all squares and on the other side it'd be all dots. This is a really big problem. Yeah, and so what you can do are these things called kernel tricks. So basically you kind of change this, you change the input of your data space and you transform it so you can easily draw a new hyperplane. And then on that new data, transformed data, you then draw a hyperplane on it. So if you see here, you have like basically two circles, right? And what probably most common SVM kernel trick is called the RBF, which is the radial basis function, which you can think of it as just like a Gaussian like normal distribution, where you can think of the Gaussian as going through like a 2D Gaussian going through like the center here, where the center is like kind of like the mean, and and it goes down. And basically what it does is that if you think about these points elevating and these points like depressing down, because this is like on the Gaussian, these are higher up and these are lower, you can now separate them. And I know these are kind of flipped, but now you can separate them, right? So if these points go lower, these points go higher, now you can have an easy hyperplane to separate them. You can't draw circles inside your hyperplane, right? So there's all types of different kernel tricks. For example, there's a polynomial, then you can even make your own, right? So that's kind of how it is, but radial basis functions I think are kind of the go-to. Your kernel trick is another example of your hyperparameter. Another one I'll talk about is the idea that this kind of linear separability is often like impossible, or if you do have it, you're really lucky. So another hyperparameter is this. It's called like I think it's like your C, or like your hardness factor. Basically saying like how important is it that all of your points are on one side or the other. And obviously sometimes it's impossible. So another hyperparameter is your C, or your regularization term, and that basically allows it to be there be some error, right? So if you don't allow that, and when there has to be error, it can cause issues. So sometimes you want to allow some error. Yeah. And so also SVMs can be used for regression as well, but they usually don't work as well. Usually SVMs are only classification, while KNNs and decision trees and random forests are all classification or regression. Now, I mean, yeah, SVMs work for both, but they're most notably used for classification. Yep. All right. So we'll stop here because we're going to go into a really big topic next. Okay, yeah. So can you explain the difference between bias and variance? Okay, so bias is so say you have some relationship, right? That is unknown. That's basically all we're trying to do in supervised learning is we want to understand some relationship that is unknown and basically create some function. Bias is the idea is that you're basically forcing it to be your relationship to be in a certain form, and it's not that form. For example, say, okay, here we can use SVM for example. Say your bias, for example, could be that it has to be linear, or has to be linearly separable, right? And say you're using a no kernel tricks, and there it should be maybe polynomial, right? Maybe this line should be curvy. Your bias error comes from the fact that you are forcing it to be linear when it really shouldn't be. You're basically giving it some type of, you're telling it what type of relationship it should be before the machine learning algorithm figures it out yourself. So, example of this is, say you're trying to use regression, and you're using linear regression, and maybe it needs to be exponential. There's going to be error from that just because you're kind of forcing a relationship to be in a certain way when it's not. Variance comes from the fact that if, for example, you have data that is very variant, and you don't have enough, you can't explain it well, it's going to be your model is not going to be able to like perform well. So basically, say you have a KNN, KNN, and the data is very spread out and very variant, and you basically say you have some holes in it. If you don't have these holes filled, it's going to perform not really well. The variant, it can explain nonlinear relationships and like complex ones, but if you have holes in basically your data is very variant, and it can vary wildly. Another example of this is maybe in your decision trees. If you have not enough data, if you include or exclude certain data points, maybe these like splitting factors change, and that wouldn't be very good, right? Obviously, if you take out 1 or 2 data points, or maybe 10 or 20ish, they shouldn't change, but that'd be a very variant model, if that makes sense. So basically, variance comes from the fact that you have not a lot of basically you don't force anything to happen, but as a result, it can your basically underlying relationship can train differently depending on what data points, and it can cause error from that. Does that explain it? I think this is a really important topic. I definitely read up on it if you're interested in this. This is probably one of the most important criteria in thinking about which model will probably perform best before you start. This kind of gives you intuition of what works. So say I'm working with a really small data set. Um, I don't want to work with really high variance models because that can cause bad results. So I might want to choose a more biased one and maybe try like figure out what type of relationship it is before. But maybe I have a lot of data and I just want to perform really well. I might choose a high variance model and low bias because then it can probably model it really well. All right, sweet Chris. Thanks for asking questions. I'll move forward. So the next big topic, so we kind of went over a couple of machine learning algorithms, but now we talk about overfitting. So overfitting is the idea is that you want the model to understand the relationship and not the noise, or basically not repeat your data points and not just copy it over. So looking at these below, this line right here would probably be a really good example of a SVM hyperplane because it separates it really well besides these two data points, and you can kind of see there's no real um, it just makes sense. Looking at it, if you were to ask someone to draw it themselves, they'd probably put something like here. However, if you look at this one fits it perfectly. However, it makes really no sense, right? If you were trying to model it yourself, you probably just put a linear line. So overfitting is the idea that you're creating too complex a relationship, or your model's creating too complex, and it resulting from it learning your training data and not learning the relationship. So a lot of times you see this from if you train your model and get your accuracy and say it's at like 95% or really high, and then you train again new data or testing on new data and it's really low, that's kind of showing you that your model learned how to predict your trained data really well but didn't generalize. So and generalizing is a very important topic in machine learning, which is the idea that this model can be given any data fitting the features you've given, and it'll get the right result. It doesn't matter that it only works for trained data. Yeah. So that's why most of the time in machine learning we have the idea of a testing set and a training set, where the training set is where we teach the model what is going on with our data. So it's basically learning, and then we get accuracy, and then we do a testing set to validate and make sure that we're not overfitting, that it didn't just learn training set, it learned the underlying relationships, and it can now understand all types of data. This is very important. And yeah, so obviously, and then let's talk about this again. So in the bias versus variance, overfitting is much more likely in a high variance model. If you think about it, if this model can perform any certain way, it's more likely to overfit and capture the data points rather than relationships. So that's another problem. That's why you need lots of data to try to stop overfitting. And we'll talk more about overfitting next time, kind of show you or let you kind of understand when that's happening. But yeah, most of the ways to fix overfitting is to maybe try to increase the bias of your model. Always adding more data points is always good. Big data is a big topic today, and it makes sense because you need a lot of data to train these models. Yes. Yeah, and so overfitting. All right, the next topic, or I think the final topic. Oh no, sorry. Final topic in terms of models is neural networks. So neural networks is the most popular models used in machine learning and in deep learning. I think we've all heard about them at some point or another. They're probably the coolest and obviously the most complex and most advanced type of machine learning we have out there. Basically, they are modeled after the human brain, where they have a model after the human brain, and so neural kind of comes from it. But as you can see, let me read it. So neural networks are one of the most popular models used in machine learning and in deep learning. They're meant to imitate the way we think, and they're designed after the neurons in our brain. The way we learn is through a series of observations, features, and eventually, after enough observations, we can determine facts, labels. While we are learning, we process these informations, looking at different scenarios and methods of trial and error in order to determine. So basically neural networks, where each of these dots are neurons, and then you can think of these lines as they're called weights, or basically connections, and basically you input your data, it goes into neurons, it processes it, and sends a signal to the next one. And then it kind of propagates through this network, and then it gives output. And that's kind of the way neurons work, is that this one fires, it goes to this neuron, and then it keeps moving forward through it, and then this electrical signal keeps moving forward. So let's talk about overview. So an observation or feature is put into the input layer. At each layer, they have a different activation function, which is applied to the values from the previous layer. It's similar to neurons firing their synapses before passing on to the next. An activation function is basically a nonlinearity function that basically most of the time will bound it between 0 and 1. So say you have weights between, or say you have input of like 100, it'll bound it really close to 1. And this allows it, this does a lot of things, but yeah, it basically makes it nonlinear, allows you to do nonlinear relationships in the model. Because at the end of the day, all you're doing is you're summing up values from the previous layer, and then you're applying this activation function and passing it on to the next layer. Before reaching the node, the values are weighted. So between each node, there's this like weights, usually between 0 and 1. Not necessarily, but a lot of time. Well, no, they're not always between 0 and 1, but they're usually relatively small if your model's training well. And these will, augment your input values or between your layers. Yeah, and so they kind of, the inputted, they're augmented by their weights. They go into neurons. They're summed, and then they pass through activation function and move on. And this kind of repeat over and over again. And then once in the training stage, once it gets output, it gets an error, and then it basically back propagates through the network and change the weights in hopes that they'll reach the right value. So they go basically, say you chose a wrong answer, it will go back and update the weights accordingly to try to get a better answer. And this basically, it's an iterative process where it happens over and over and over again, hundreds and hundreds of times, if not hundreds of thousands of times. And it basically keeps doing this until it converges to the best solution. So you can kind of see this is a really simple one where you have your inputs, where x1 to xn is your feature. So for example, it's like maybe like HP, special attack, all the way down like maybe defense. And your weights is the things that your neural network is updating to try to get the best answer. And where x0 is like a bias unit, which is not a feature, but just basically allows you to like think of it as your intercept. And it basically allows you to add some additional values. So basically what it does is that you take your inputs, multiply it by your weights, and then you sum them together. And then, as you can see here, and then you do this activation function that makes it nonlinear, and then it predicts it. So, for example, here, this is like a good example of activation function. Say we were trying to predict whether it's legendary or not. Most likely, almost 100%, that these weights, when they're summed and add together, are not going to be between 0 and 1, where 0 and 1 is a probability that's legendary. So if you add it through this activation function, it allows it basically to become a yes or no answer, where, for example, if you have 0.6, it's like 60% probability that's going to be right. And so once it gets the answer, it will, if it got it right, cool beans. But if not, it will take this, calculate this error, back propagate, and then update all the weights. And it just basically keeps doing this over and over again until it converges to answer, or until you think the solution is good enough. So any questions? I'll go over some of the terminology. Alright, cool. So channels and weights. So connecting each layer, node to node, are channels. There's a channel with a weight connecting to each node from the previous layer to each node in the next layer. So, just these lines right here, and basically each of them have a weight associated to them. The inputs from the previous layer are multiplied by their corresponding weights, and then those weights are summed up at the next node. Bias is basically your intercept, or basically just adding some value to it that's not associated with the input. This is sometimes pretty important, other times not really. Activation function, this is a threshold function that determines which neurons will be fired or continue to pass their value. So for example, maybe if this is between 0 and 1, if it's about 0.5, it'll fire, and so on and so forth. Yep. Backpropagation, this is the process, this is like basically the learning, and this is like how it converges to a good solution. It's a process of going back through the network and changing the weights between layers. That way when the new data is fed through the network, it will get closer to reaching the desired output. The weights are changed determined from the out whoops, the weights are changed. How the weights are changed are determined from the error and how far the output is from the target. All right, and then some other stuff like batch size, for example. Um, um, I guess let's go into this. So you can either feed this one input at a time and then get the error, which is called online learning. But however, if you think about it, maybe you have like a million data points. This will be pretty slow and it can be really noisy. Because if maybe one data point shifts your solution one way and then next way and it keeps bouncing back and forth, but batch learning is the idea that you will pass through multiple examples and then take the average of their error and then use that average to update the weight. So basically, it's the idea that you have maybe more a smooth learning process. Um, and yeah, so this basically allows you to like maybe converge to a solution faster. And batch size can be as big as the entire data set, so you can take the average of the entire data set, which is called like stochastic gradient descent. Or you can do like mini batch stochastic gradient descent, where you may take like samples of like 16, and this basically allows you to get some individual data points, like features like relationships, but not taking a really long time. So I don't get too much into the batch size, but you don't have to do one at a time. You can do it multiple at a time, and you can average the error. The next thing is a cost function optimization. The cost function is basically how it's going to get that error. So easy cost function is just the predicted output versus the true output. That's usually not that good depending on the algorithm. A lot of times you can use something like um, you know like um, like cross entropy or mean squared error, all those kind of things. So there's many type of cost functions out there, and depending on the problem, you want to probably change it. And optimization is basically the way or how it tells it to update the weights. An epoch is basically once you fed all the data through one time, that's one epoch, and most time you have multiple epochs. So just because you feed each data point at once, it doesn't mean it'll converge. You may have to do 10 to hundreds of epochs for each time you're feeding the same data points in randomly. And yeah, so basically you're feeding data points in successfully, but also once all the data points are fed in, you're going to repeat that process over and over again. And these are called epochs. So you have batches within your epochs. Hyperparameters is probably the hardest part of neural networks because neural networks are they're very customizable, and you can basically determine the number of nodes, the number of layers, the activation function, the initialization of the weights, all kinds of things. There's a lot of things. There's not a lot of knobs in neural networks that you can change, and that allows you to get really good solutions really well. And yeah. So there's a lot more neural networks and the basics of how they function. There are hundreds of different types of functions and use cases for them, but to go over all of them is beyond the scope. Yeah, so I just want to give kind of, I think, yeah, there's a lot of things you can do in neural networks, and they can be augmented in a lot of ways. They're not always just these neurons. There are different types of structures. Say, for example, when you're using pictures, you can use something like convolutional neural networks, which is a type of architecture, and there's recurrent neural networks, which is like basically goes back in time. Say, for example, you're predicting stock prices, you might want to know the stock of the price last day or maybe the month ago. So you want to go back in time and use those values as well. That's called like recurrent neural networks. There's like natural language processing neural networks, all kinds of stuff. So definitely within each domain, there's a lot of different things you can do to it, neural networks to augment them to better suit your problem. All right, any questions before we move on? And here, I'll link this YouTube video in the chat because I don't want to play YouTube video and get copyright strike, unfortunately. Yeah, just a 5-minute video about neural networks. I definitely recommend it. I also would recommend there's a 3 brown, 1 blue. It's a math channel. They kind of explain how neural networks work. I think they give you a really good visualization of how they work and kind of understanding of what's going on. But yeah, if there's no further questions, we'll move forward. I know neural networks seem like probably the most confusing, but just think of it as you take values, you multiply by some weight, you sum together, activation function, next layer, and so on and so forth. Yep. Let's move on if there's no further questions. All right. So, okay, creating, training, and testing data sets. So, data can sometimes be hard to get or very expensive. All data that you have, or the data that you have is all you can get. So you need to be able to do what, basically use all that what you have available. When training a model, you can't use all of your data, otherwise you have no way to evaluate it without getting more data. The best way to do this is using the train test split, which is basically allows us to be alerted if we're overfitting, where we have a training set that teaches a model the relationship and the testing set that we can then run through the model and make sure that it's performing well regardless of the data. So previously we had the targets, targets, which was the legendary or not, and the features, which was HP, those kind of things, right? Where we have 800 samples and we have 11 different columns, right? And then our output or our target is just 800 yes or no, legendary or not. So from scikit-learn, I don't want to code today. We'll go over this again in ML0. We're going to use a train test split function where basically input your x and y, and basically it randomly selects 33% of your data points out of your 800 to be in the testing set where you have x test and y test. And you can see here, this is about 33%. And now you're going to train using x train, and then x train and y train, and then you're going to test using x test and y test. So train the model. We're going to go over this more next time, but basically you can use the .fit function, any of the models in sklearn, and it will start. Sorry, headphones turned off again. It'll start like learning relationships and basically doing all the work for you. So you don't. It's all machine learning, as the name says. It's all automatic. All right. So once the model is trained with our training set, now we want to predict or evaluate our testing set and make sure we get the same accuracy, for example. So if our training has accuracy of 75% and our testing set gets 72%, we're not overfitting, but say we have significantly lower, we have overfitting, we might want to either change our model type or something like that. Also, using all the testing sets, we can also see okay, which model is performing best. This will kind of allow us, we talked about SVMs, KNNs, random forest, decision trees, neural networks. This will allow us also to choose which one's the best for our problem. All right, the next step is tuning hyperparameters. So this is kind of, this is, I think, parts 7 and part 5 are sometimes can be done together. But basically the idea is that neural networks have all those, or neural networks, any of the algorithms have their internal knobs that we can change to make them perform better or worse. And those are our hyperparameters. So remember, KNNs, we talked about the n neighbors or k neighbors. And then we can different types of metrics, which is how we're going to measure distance. And then all of the other ones. So we can change these within our algorithm to see if they do better or worse. For example, our kernel, using our kernel trick, our C, which is our hardness or regularization term. And for example, random forest, we talked about n estimators, which is the number of decision trees we use, criterion, all this kind of stuff. So, and bootstrapping, for example, if we want true or false, all that kind of stuff. And there's other things as well. For example, njob, which is how njobs, which is how many processors your computer uses. For example, you're doing multiple decision trees at the same time, so you can parallelize it. Random state, there's some randomness aspect to it, so you can set it so it's repeatable, all that kind of stuff. So yeah, so you do step 5, you train it, you evaluate it, and then you will maybe update the hyperparameters, and you kind of repeat this process over and over again until you probably get the best parameters. And you do this for all the models, and then at the end you'll have all these super optimized problems or optimized algorithms, and you can now say you have the best model. Um, I will say that you can optimize all of the models relatively fast besides neural networks. Neural networks, it's since it's so open-ended and um, like basically so basically just open-ended. You can basically choose any neural width, so how many layers you have and any height, how many nodes you have in each layer, and infinitely many combinations. That a lot of times it's not so definite, but you can kind of tell based on testing. So if you add a layer and it does worse, you probably shouldn't keep adding layers, stuff like that. So there's ways to know, but it's a little hard to optimize their own networks. Anyways, so this is kind of the end of ML0. We kind of went at a very, very, very high level. This is by no means comprehensive um, over some of the steps in creating a model, machine learning model. Talks about kind of what each model does and how it performs. And yeah, kind of talks about at a high level. Next week in ML1, which we'll be doing next Monday, we'll be going over how to actually code them. We'll going over a real life example of how we can implement these models to perform well. I definitely recommend next week. Now that you have all this good knowledge, it's gonna be really cool. So I'll stick around for another like 5-ish minutes. Answer any questions in chat. I'd love to answer. And if you haven't signed in already, please sign in. I definitely appreciate it. And so with DSI. Also, please follow us on our Facebook for our future or to let you know when future workshops are happening. And I think that's it. I'm gonna just stay around a couple minutes, answer questions if there is any. Yeah, this will be posted on YouTube later. Alright guys, I think since no one's asking questions, I'm going to stop for today. Feel free to reach out to me on LinkedIn. My name's Simon Frank. If you have any further questions, or you can email DSIUFL and we will try to answer as well. We'll be back next week for ML1, which will be going over implementation of these machine learning algorithms. And yeah, have a good day, everyone. Thanks for coming out. I really appreciate the interaction. Good night, guys.